Okay, so welcome to the second part of this video wherein we subdivide the classification of machine learning into two parts. So first we have to talk about the first three classification algorithms. First we have KNN or the K nearest neighbors. So the idea of this is that we classify a data point based on the majority class of its K nearest neighbors. For example, we have here a graph in a two-dimensional plane, but it could also be a three-dimensional, depending on your labeled data or unlabeled. So for example, we have three classes, and these three classes, they have 2 points or two inputs. So let's imagine like if you want to say predict or classify if this is class A, B, or C, then mo ni siyang iyahang mga inputs. So say for example, class A is like the basic example is if the students will pass or fail. So, delete kasi tatlong classification. Example, if, ano kaya maganda? This class A here has this kind of disease. So this is A, this is B, and this is C. So we plot the points. Now, for example, in a data, we have three classes there. So in a data, we have inputs of, for example, it's blood sugar. Ano ba? Blood sugar and your, say for example, height. I don't know. So for example, the blood sugar and height are these points right there. So we plot this blood sugar and its height and the person's height. Then we can already have this plots here, classes A, B, and C. And then we train this data into using KNN algorithm, and then it can already classify which class or which disease you have having uh, having an input. So for example, your blood sugar is 7 and then you have a height of 168 centimeters. Mataas na sugar, 7. So you belong to, say for example, class B, and this class B has something disease. This is how k-nearest neighbors work. We plot each inputs and we predict based on that input using this kind of graphs right here. So there's a P here, which is the baseline. So one example is to classify a student's performance as pass or fail based on similar students. So in a plane, when we have pass or fail, of course, the pass students are labeled here, and then the failing students are labeled here. Say that's class of passing students and failing students. So of course, the predictors there, we have its scores in summative assessment and its attendance. Say for example, mo na siyang variables that could predict if the students pass or fail. So attendance and summative assessments, these are good predictors if the students pass or fail. So say for example, we plot it there. These are the scores of ano siya ang scores. See y variable, and this is the attendance. How many number of classes did you attend? So of course, the higher attendance, dito dapat din, dili siya. The higher the attendance, the higher you learn, the higher you have your score. And then the failing students, the lower the attendance, the lower the summative scores. This is where they should be plotted. So yeah, obviously, we can use KNN for this type of classification. Okay, so in engineering, we have classification of soil samples as stable or unstable based on geotechnical properties. Classify machine parts as defective or non-defective using vibration sensor data. Next, please watch this video about the k-nearest neighbors.
K-nearest neighbor is a super simple supervised machine learning algorithm that can be solved for both classification and regression problem. Here is a simple two-dimensional example for you to have a better understanding of this algorithm. Let's say we want to classify the given point into one of the three groups. In order to find the k-nearest neighbors of the given point, we need to calculate the distance between the given point to the other points. There are many distance functions, but Euclidean is the most commonly used one. Then we need to sort the nearest neighbors of the given point by the distances in increasing order. For the classification problem, the point is classified by a vote of its neighbors. Then the point is assigned to the class most common among its k nearest neighbors. K-value here controls the balance between overfitting and underfitting. The best value can be found with cross-validation and the learning curve. A small k-value usually leads to low bias but high variance, and a large k usually leads to high bias but low variance. It is important to find a balance between them. For the regression problem, we simply return the average of the k nearest neighbors labels as the prediction. Here it is.
Yes, so the coding part for these k nearest neighbors will be talked about in your AI lab. And we will have examples for it as well. Okay, so let's move on to the next slide.
K
And that
nearest
would be the decision trees. For decision trees, as you can see in the graph, it splits data based on features into a tree of decision. For example, very common example is kana sa hospitals, diagnosing flu based on symptoms. So, di ba mangutan ang doctors sa mga sakit-sakit, and then do you have this or that, na ba kay allergies, and then that leads them to diagnosis. So there's like a decision tree on the result or classification afterwards. So it's example in engineering applications, we have predict power system faults, if there's a transformer failure or is it a stable operation, and determine whether a project construction should proceed based on budget, soil type, and risk factors. That's also one for our CE friends. Decision rules for hardware troubleshooting as well. So these are very common types of decision trees. So, for example, in the weather, we have there is sun, there is a cloud, and there is a rain. So if it's sun, would you want to go out for less than 30 minutes or 30 minutes? And if it's very hot, then should you walk or should you take the bus? So things like that, like everyday decision that you think about is like a decision tree, and it leads you to a diagnosis or a decision rather. Yeah, like those decision. So for 1 minute, kindly watch this decision tree analysis.
Decision tree analysis is a value management.
Hold on, let me check if this includes.
Management planning process that allows you to identify and examine uncertain situations in a visual way and choose the best options going forward. At the center of this process is, of course, the decision tree. A decision tree is a flowchart-like diagram that shows the various outcomes from a series of decisions. A primary advantage of using a decision tree is that it is easy to follow and understand. Decision trees have three main parts: a root node, leaf nodes, and branches. The root node is the starting point of the tree, and both root and leaf nodes contain questions or criteria to be answered. Branches are arrows connecting nodes, showing the flow from question to answer. Each node typically has two or more nodes extending from it. A decision tree can be used in either a predictive manner or a descriptive manner. In either instance, they are constructed the same way and are always used to visualize all possible outcomes and decision points that occur chronologically. Decision trees are most commonly used in the financial world for areas such as loan approval, portfolio management, and spending. It can also be helpful when examining the viability of a new product or defining a new market for.
Yeah, so you have heard like in the video wherein it a common example is in finance, right? So should we give loan to this person here? There's this thing called decision tree to analyze. So does this person spend more than his or her own salary? how much is his or her salary monthly or yearly, things like that. So there's a decision branches in each node or in each questions that we have.
Existing product. Decision tree analysis can also be a powerful tool for managing projects. Project managers need to be able to identify all possible scenarios in the project lifecycle. Each decision point could lead to success or failure. Evaluating all foreseeable outcomes and weighing their risks and benefits is a crucial step in the planning process. Every project is different and requires a customized analysis. Here are some best practices when creating a decision tree diagram. Start with a rectangle near the left edge of the page to represent the first node. In this rectangle, write the first question, main idea, or criterion that will lead to a decision. For every possible alternative, draw a separate line that begins at the node and moves away towards the right of the page. Using a loan approval process as an example, the first node may have been income, and the associated branches might be less than $50,000, $51,000 to $100,000, or greater than $101,000. At the end of each branch, add a leaf node. Fill each of these leaf nodes with another question or criterion. Repeat the process of adding a branch for each possible alternative leading from a leaf. Label each branch just as before. Continue adding leaves and branches until every question or criterion has been resolved and an outcome has been reached. Finally, consult with all stakeholders and an outcome has been reached.
So it is stuck here, the leaf nodes. So it is what it was mentioned that you continue assessing the customer based on his or her credit history, and under the credit history, does he or she have a high risk of credit history or good credit history or unknown? If unknown, how much is his debt? So you have to consult the stakeholders as mentioned here to verify the accuracy of the content of your decision tree. So for example, you're going to have a project on finance. Of course, we are not accountants, we are not business people. So we have to be able to consult with the experts, especially on medical diagnosis, right? So for the next classification of machine learning, we have what we call the naive Bayes. And the idea of naive Bayes is that it uses the Bayes theorem, assuming independence between failures. So in statistics, we have the probability, right? And one general example for the naive Bayes is the spam filtering. So are the keywords here spam or not spam? So what engineering applications include the predicting if a chemical process run is safe or unsafe based on sensor readings, classifying equipment maintenance logs into normal or critical categories, or email filtering for phishing detection. So the idea of naive Bayes is heavily falls on probability, and I would want you to watch this wonderful explanation of naive Bayes in an animation.
It is easy and fast to predict a class of its dataset. It also performs well in multi-class predictions. Let's take a look. Hey guys, and welcome to another fun and easy machine learning tutorial on naive Bayes. It's a good day to play golf, or is it? Let's take a look at some of the factors that determine whether or not we play today. These features are weather conditions or outlook, if it's sunny, overcast or rainy. There's also temperature, humidity and wind. Please smash the subscribe button and click the bell icon to join our notification squad. If you think about it intuitively, we are more likely to play when it's not too hot or cold, which means overcast and mild temperatures. If it is less humid with minimal wind speeds, we are more likely to play. If it's too hot or sunny, we may become exhausted very quickly. Let's take a look at our dataset. So if we recorded our circumstances over 14 days, we have our outlook, temperature, humidity, wind speed, and our dependent variable, which is whether or not we play golf. The objective here is to estimate the likelihood of playing golf, yes or no, given weather condition information. So based on this data, let's see how we can approach this problem using the naive Bayes algorithm. First, we determine how many yeses and how many nos we get from our dataset. So the probability P of C, or probability of our classes, which are yes and no, we can calculate this as follows. So the probability of yes is 9 out of 14. We can count 1, 2, 3, all the way to 9 total yeses from the 14 possible days. And similarly, we can count 5 no's, which gives us a probability of 5 out of 14. Now we also need to calculate the individual probabilities with respect to each features or weather conditions in our dataset. So for sunny, the probability that it is sunny given that it is yes is 2 out of 9. So P sunny given a yes. Why? Because from 9 yeses, it is only sunny twice, as we can see over here. To calculate the probability that it's sunny given a no is 3 out of 5. So from the 5 no play days, only 3 days were sunny. For the overcast outlook, we can do the same for both yes and no classes. We count 4 days that we got a yes and 0 days that we got a no. So the probability that it was overcast given a yes is 4 out of 9. And for not play class, we got 0 out of 5 respectively. Now we can compute these probabilities for all the other features. You can see how easy this is. So assume we need to classify the following new instance, where the outlook is sunny, temperature is cool, humidity is high, and it's a tad bit windy. Should we go out and play some golf, or rather stay indoors and watch a movie? Firstly, we look at the probabilities that we can play the game. So we use our lookup tables to get the probability that outlook is sunny, given play is a yes, is 2 over 9. Probability of temperature equals cool, given play is a yes, which is 3 out of 9. And similarly for humidity and wind, we have 3 out of 9 for both of them. And then we have probability that play is a yes, is 9 out of 14, as we discussed earlier. Next, we consider the fact that we cannot play a game. So for outlook equals sunny, we get 3 out of 5, temperature equals cool, 1 out of 5, humidity 4 out of 5. Wind equals strong, given a no is 3 over 5. And then play equals no is 5 out of 14. Then using those results, you have to multiply the whole lot together. So you multiply all the probabilities for play equals yes, such as the probability that x given play equals yes, multiplied by play equals yes. So that is 2 divided by 9 by 3 over 9 times 3 over 9 times 3 over 9 times 9 over 14. And this gives us 0.053. And this gives us a value that represents the probability of x given a class times probability of a class. Or in this case, we have probability of x given play equals yes times probability that play was a yes. We also have to do the exact same thing for play equals no. So the probability of x given that play equals no times probability that play equals no. That equals 3 divided by 5 times 1 over 5 times 4 over 5 times 3 over 5 times 5 over 14. And this gives us 0.0206. And finally, we have to divide both results by the evidence, or probability of x, to normalize. The evidence for both equations is the same, and we can find the values we need within the total columns of the lookup table. Therefore, probability of x equals the probability that outlook was sunny times probability of temperature equals cool times probability that humidity is high as well as wind equals strong, as we mentioned earlier. And this gives us our probability of x, which is 0.02186. And then dividing the results by this value, we get the probability that we played golf given x, and this gives us 0.2424, as well as probability that we don't play given an x condition, where we get 0.9421. So given the probabilities, can we play the game or not? To do this, we look at both probabilities and see which one is the highest value, and is our answer. And therefore, since 0.9421 is greater than 0.2424, the answer is no, we cannot play golf today.
Yeah.
Probably.
So it was a long video, right? But pretty much it delves heavily on the inputs and probabilities. So you see, there are inputs here such as the outlook, the temperature, humidity, and windy. So say for example, if if the this is our data set and we train them, and then afterwards we would use this data set, or we would use the model using this data set if we want to play golf today or not. So when we go outside, we look at the outlook. Okay, it's sunny. The temperature is hot. It has a high humidity and it's not windy. So of course, okay, I won't play golf. Something like that. Because using probability and the model, it gives us a numerical value result. So using this numerical value results, using naive Bayes, it will give us a prediction whether or not to play golf or not. So that is pretty much the idea of a naive Bayes. So the next three classification algorithms will be on this will be on the next part of the video as well. So thanks for watching.